Previously, on many-body quantum mechanics, we learned that if you have a single particle, then obviously you can write that state as a linear combination of its basis states. That's what a basis state means. But if you have n of those particles, then the appropriate Hilbert space is the tensor product of all the otherwise identical Hilbert spaces for those individual particles, and so the basis becomes every combination of the basis states for the individual particles, and then we have this very large tensor product Hilbert space. And that means you need an individual coefficient for every possible combination of indices for our single particle basis there. Now we also learned something very important about indistinguishable particles. If those n particles are indeed all the same and they're all fundamental particles, then there's absolutely nothing to tell the difference between them. And that means that if we interchange any two of them, we have to get exactly the same physics. And we learned that that means that the best we can do when we interchange them is that we have to either get a plus sign or a minus sign on our coefficients. So we have an enormous symmetry, which is for bosons, or antisymmetry for fermions in those coefficients, and so a large number of these coefficients here are redundant. And rather than live with a situation where we can write down states that don't have the correct symmetry, so we can make mistakes in how we write these things down, what we did instead is we invented a notation where the symmetry or antisymmetry was built in fundamentally to the description of the state itself. And so the coefficients of those things, those coefficients are actually independent. They're just normalized in the normal way. And this notation is called occupation number notation. Some people call it second quantized notation for historical reasons that don't really mean anything. So if we want to deal with this occupation number notation by preference, then it turns out that the best way to deal with operators in that notation is to build them out of creation and annihilation operators. These things here. And creation and annihilation operators for bosons work exactly the same way as ladder operators work for harmonic oscillators. For fermions, they work in a similar way, except instead of commutation relations being given by this, you get anti-commutations being given by that. If you're building things out of these creation annihilation operators, a very common thing to use is the number operator, which is just delete one, then create one particle, and it turns out that just gives you the eigenvalue of the number of particles in your state. Now, if we're going to deal with creation annihilation operators instead of our original form of operators, then we're going to need to know some way of translating all the operators we had in our original notation into this occupation number notation. For all common forms of operators, that translation is surprisingly easy. Let's imagine we have some operator, which is the sum of a bunch of separate operators for the individual particles. An example of that might be, say, a Hamiltonian, where all the different particles don't interact at all, and so they all just live with their own individual Hamiltonian. And we could extend that by possibly having extra terms where we have interactions between pairs of particles. We have to sum over all non-identical pairs of particles. Let's expand this operator into a basis for the single particle states. But because these states here are a basis for the pth particle, then these things here are a basis for the operators acting just on the pth particle. And similarly, these things here are a basis for the combined Hilbert space for the particles p and q. So all we need to describe this operator in general are these coefficients. And these coefficients have indices which describe which states we're coupling between, but they do not have indices which describe which particle. So there's no p index on those coefficients, and there's no p and q index on those coefficients. Now why is that?